Okay, so welcome to the fourth day of the high-frequency gravitational wave workshop. This is, of course, the highlight of the workshop because today will be the social dinner. But another highlight will, of course, be the talks, and we are going to start with Tao Liu on detecting high-frequency gravitational waves in planetary magnetospheres. Please.
Can you hear me? Yeah. Okay, very good. Before I start, let me thank first for this invitation. In this talk, I will focus on the detection of high-frequency gravitational waves in planetary magnetosphere. But I will
the button in the middle?
Yeah.
On the mouse with the mouse.
Okay, thank you.
The one in the middle goes forward, the one at the bottom goes backward.
Okay, very good. Okay, so I will try to make my talk general. Okay. Let's start with some basics about the inverse Gerstenstein effect. As mentioned by Camilo yesterday, Gerstenstein effect was suggested in 1962. And this effect is based on the Maxwell theory in the framework of general relativity. And its inverse version tells us, while propagating in an external magnetic field, the gravitational wave could oscillate into photons due to a state mixing. This sounds like neutrino mixing. And at a leading order, this effect can be described by a mixing matrix. And here, the delta M is proportional to the external magnetic field. It is a measure of the mixing effect. And as for the delta gamma, it denotes the effective photon mass without such a mixing. And here, the delta gamma receives two types of contributions. The first one is related to a vacuum effect. And this effect is proportional to the frequency of the photons. And another contribution is from the plasma mass. Okay. And this contribution is inversely proportional to the frequency of photons. And for a general magnetic field, the conversion probability from the gravitational waves to the photons can be calculated by performing this integration along the path of the gravitational wave traveling. Okay. And if we go to homogeneous magnetic field, then we will have a much simpler format for this calculation. And in this formula, we can say here is a prefactor, and this prefactor is completely determined by the profile of the experimental setup. And in addition to that, there is a square of the single function. And the value for this factor is maximized in the case where the oscillation length is the oscillation length between the gravitational wave and the photons is much bigger than the capital L. And here, the capital L denotes the characteristic travel distance of gravitational waves in the magnetic field. Okay. And this scenario is usually dubbed as coherent conversion. And from this discussion, we can say for ideal experimental setup, okay, the coherent conversion should be achieved. Okay. And here somehow you may say, well, somehow this formula is obtained in for homogeneous magnetic field, but later actually you will see this formula is very helpful for us to understand what happens in various scenarios. Okay. Okay, then for a given detector, the calculation of the signal photon flux is standard. And here, the angular distribution of the gravitational wave converter photons is determined by this by the conversion probability. You see here it is dependent on the directions of the gravitational wave path. Okay. And another thing to note is in this formula we can say only the photons falling to the detector field of view can contribute to the calculation of this signal photon class flux. Okay. And then based on that, we can calculate the total count of the signal photons. This is straightforward. And here the P square bracket represents the average conversion probability within the field of view of the detector. And story is also similar for the count of background photons. And then just follow some standard statistical method. We can set up a limit on the characteristic string of gravitational waves. And from this formula, we can say the limit will be stronger if the effective area of the detector is bigger, the observation period is longer, if the field of view of the detector is broader, and if the conversion probability is larger. Okay, so this is consistent with our expectation. Okay. Okay, and in last decades, the inverse Gerstenstein effect has motivated broad classes of proposals about the detection of high-frequency gravitational waves. And here, the magnetic field involved could be either artificial or astronomical. And as said, in this talk, I will focus on magnetosphere. Okay, for this purpose, let's consider two representative cases. The first one is a neutron star, and the second one is Earth. Let's make a comparison about the features of these two types of astronomical objects. And later we will say these features can have significant impacts on the detection of the high-frequency gravitational waves. And here we know the neutron star has extremely strong surface magnetic field. It can be as large as 10 to 8 to 10 to 15 Gauss. Okay. As a comparison, the surface magnetic field for the Earth is much, much weaker, just about 0.5 Gauss. Okay. And in addition to that, the spinning of neutron star is relativistic. Okay. And then given such a boundary condition, Goldrich and Julian found that the plasma density for a neutron star can be well described by this solution. Okay, and nowadays this solution is called GJ model. And as for the Earth, its spinning is highly non-relativistic. Okay, and as a first order approximation, its plasma density can be described by the barometric model. Okay, and here is analytical profile for the barometric model. Okay, and in addition to that, we know neutron stars are distant from the Earth. And to our knowledge, the neutron star closest to the Earth has a distance to the Earth about 100 parsec. Okay, this is the closest neutron star known to us today. And as for the Earth, well, we live on the Earth. Okay. The conversion of the gravitational wave into photons in the neutron star magnetosphere has been studied in this classical paper by Raphael and Stodowski. Okay, and to my knowledge, this is probably the first paper exploring this possibility. And here, as said, we want to use this formula to understand to establish a physical picture in various scenarios. And this formula was derived for homogeneous magnetic field. But in this setup here, the capital L can be approximately interpreted as the geometric size of the neutron star. Okay. And now let's go through the features of the neutron stars one by one. Okay. And as said, the magnetic field for near the neutron star is extremely strong. And then this implies that the delta M has a large value. Delta M is, just recall, it is the measure of the mixing effect. Okay. And certainly this will bring us an overall enhancement for the factor of the conversion probability. Okay, I'm talking about this prefactor. But on the other hand, we should also realize that a big value for delta M can greatly suppress the oscillation lengths between the gravitational waves and the photons. So in this scenario, it is difficult to achieve a coherent conversion. And then what does that mean? That means, okay, given the magnetic field, actually we cannot give a full plane to such a magnetic field. Okay. Actually, the story can be even worse for the low frequency region. This is because somehow the contribution from the plasma is inversely proportional to the frequency of photons. Okay. And then in such a case, you can see somehow the oscillation length can be further suppressed by the contribution from the plasma. And then probably you can say, okay, then you are talking about the surface of the neutron star. Then how about story if we go to the sky of neutron star? Okay, and where probably the plasma density is not that big, then its contribution can be small. Okay, but here the story is for GJ model, as the altitude increases, actually the plasma density decreases not that fast. Okay, so because of that, such an effect actually is not significant. It's not so significant. Okay, and in addition to the impacts on the conversion probabilities, and another feature about neutron star can also influence the detection efficiency. This is distance. What is the reason? Okay, just think about it. The signal photons can be only produced near the neutron star, right? And because the neutron star is very far from Earth, so the angular distribution of the signal flux actually is extremely tiny. Okay, and because of that, the effective field of view actually is also quite small. And then how about story about the conversion in the Earth's magnetosphere? Okay, let's take a look. And this was explored by our collaboration recently. And again, we'll use this this formula to demonstrate the physical picture. Okay, firstly, for the Earth, its surface magnetic field is very, very weak. Okay, and then in such a case, the value of the delta M is also small. But on the other hand, it is also valuable to note, despite all this smallness, the suppression effect from delta M to the oscillation length between the gravitational wave and the photon actually is also small. And then you may ask, then how about the contribution of the delta gamma? Okay. Yes, delta gamma receives two types of contributions. One is based on the vacuum effect, and another one is related to the plasma mass. Okay. And here the point is, for the contribution from the vacuum effect, it is not so important until the frequency of photons is extremely high, which is out of our interest. Okay? And as for the contribution from the plasma, okay, let's go to the barometric model. And different from GJ model. Okay. So for the barometric model, as the altitude increases, the plasma density actually is suppressed exponentially. Okay. So this implies that this contribution can be important only for the region where the frequency is relatively low and the altitude is not that high. Okay. And in addition to that, we live on Earth. This means that we can place the detector inside the magnetosphere. And for that case, you can imagine the signal photons can come in all directions. Okay, so the angular distribution for the signal photon flux is wide. So in this sense, the luminosity is effectively increased. Okay. And then you may ask, oh, how about the other? How about other astronomical objects with magnetosphere? Okay, very good. For example, like Jupiter, like a Sun, like a white dwarf. And here I would say for the Jupiter and the Sun, okay, their properties are pretty much Earth-like. Their surface magnetic field is relatively small, and their spinning is non-relativistic. And also, they are not very far from Earth in the sense of astronomical distance. Okay. And as for the white dwarf, somehow the story is a little complicated. It's kind of a mixture between these two types of systems. Its spinning is non-realistic, but somehow it is also very far from the Earth. Okay. Okay. And based on these discussions, we can say if we set these astronomical objects as a laboratory, then we can use electromagnetic astronomical telescopes to perform the detection. And one interesting thing about this idea is somehow the covered frequencies by this method forms a nice complementarity with the ones of the low frequency detections. Okay. And then the question left is just, okay, what kind of sensitivities can we achieve? Okay, certainly there exist multiple possibilities about how to operate such a detection. And as a demonstration, here let's consider a satellite-based detector for a planet, especially for the Earth. Okay, and then for such a detector, we can build up instant coordinates. Here, the z-axis pointing from the detector to the center of the Earth. And then we can separate the directions of signals into two regions. One is planet cone, and another one is outer space. Somehow this separation depends on whether or not the line of sight intersect with the surface of the planet. Okay, and then in this plot, we choose the dependence of the conversion probability and the polar angle in such a framework. Okay, and from this plot we can see the conversion probability peaks sharply at the boundary between the PC region and OS region. And also, as the attitudes of the detector increases, somehow the conversion probability increases, but at the cost of a smaller cone. Okay. And for the demonstration of the sensitivity, okay, we will consider two benchmark scenarios.
Sorry, quick question. So in the previous thing, is this a probability or a power? Yeah, this.
Sorry?
Is this a power or a probability?
What is?
What is the y-axis?
P.
Oh, P. P is a probability.
How can it be larger than 1?
Oh, it is somehow, we introduce some normalization factor. Okay. So here it is, okay. Sorry. Sorry for this confusion. Okay. Okay. Next, let's say how to okay. Next, let's say the sensitivity analysis. For this purpose, we'll consider two scenarios dubbed as conservative and optimistic. Okay. And we will let the detector operate at a low Earth orbit and observe in the dark side with the bird view. Okay. And as for the effective area and field of view of the detector, in the conservative scenario, we let them to follow the profile of existing missions, and in the optimistic scenario, we let them follow the profile of the future telescopes. And then the target will be the isotropic stochastic background of high-frequency gravitational waves. Okay. And as for the backgrounds, And the one class of main background will be the albedo reflection of cosmic photons. The cosmic background photons have been well measured in the last decades. Okay, so from this plot, somehow you can see the strength of this background over a broad frequency, and here is CMB. Okay, and another important background will be from the atmospheric thermal emission, but for this class of background, they will mainly contribute to the infrared frequency band. Okay, so this is a master plot, and from this master plot, we can see encouraging sensitivities for broad range of frequencies, including a large portion unexplored before, can be achieved. But here, we should also realize that a big gap still exists between the project sensitivities and the BBM band. Okay. And in addition to this, in our study, we also analyzed a limit from the neutron stars based on the M7 X-ray dim isolated neutron stars. And here is a limit. And something interesting is roughly at the same time, Asuka and his collaborators performed a more dedicated study on the neutron stars. And this is a master plot from their paper. And if you compare the X-ray bands, then you will see somehow the sensitivities are comparable. Okay, before I close this talk, let's take an outlook. And in this study, as said, somehow we let the detector to have a bird view, but there exist other possibilities. For example, we can let the detector to look to the sky, okay, look to the outer space. Actually, we can have potentially we can have some gain from such a possibility, especially for the infrared frequency band. As said, for this region, somehow the sensitivity is influenced a lot by the atmospheric thermal emission. But if we let the detector look to the outer space, then such an effect could be suppressed a lot. Okay. And in addition to that, we have nice radio telescopes. We have nice next generation telescopes, FAST and SCAR. And FAST is the largest single-dish radio telescopes located in China. As for SCAR, it is an international program. And certainly it is interesting to extend the sensitivity studies to the radio band. Okay. And finally, we can also extend the study to Jupiter and solar missions. And compared to the Earth, Jupiter and the Sun have a stronger surface magnetic field. And also, due to their larger geometric size, the gravitational wave photon conversion path is also relatively longer. Okay. However, in order to have accurate estimate about the sensitivity potential for this methodology, there are still a list of questions yet to be addressed for the next step study. And for the signal, for example, for the signal rate calculation, we should go to the more accurate description on magnetosphere. Okay. In this study, for example, we use a dipole model for the magnetic field, but there exists a more accurate description about the magnetic field of the Earth. This is international geometric reference field, and for this model, multiple sources for the magnetic field have been considered. And in addition, we should also improve the description of the plasma density profile. And as for the calculation method, in our study, we simply use this one-dimensional calculations. And in a nice paper by Sebastian and their collaborators, they point out.
That's not me.
Not you?
As much as I'd like to take credit for that paper, that one's by Sebastian Baum.
Oh, okay, sorry. Okay, sorry. Okay, sorry. Okay. Okay, let's focus on physics. Okay. And in this nice paper, it was pointed out somehow the plasma effect. The plasma can contribute to the dielectric tensor of the media. And this effect somehow, okay, and because of this contribution, somehow the transverse mode and the longitudinal mode of the photons can be mixed with each other and hence modify the transfer of the energy flux, okay. And this effect could be important for the gravitational waves with the radio and relative low frequencies, okay. And in addition to that, we should also improve the reconstruction of background. We don't have simulation tools like Magnetosphere, so dedicated efforts are needed in this regard. And also, we should consider how to optimize operation plans. For example, for the satellite-based detection, how to optimize the design of the orbital. And for the ground-based detections, how to suppress artificial noises. Okay, very good. Okay, here are the take-home messages. Since I've already run out of time, I will stop here. Thank you for your attention.
So thank you for this interesting talk. So as before, we have now a little bit of time for questions immediately on the talk, and then of course there'll be more time for discussion later on. Yeah, Camilo?
Yeah, so can you elaborate a bit more on this barometric formula?
1 second. So you are talking about the sensitivity formula, or?
The barometric formula. So you've
barometric
modeled the
formula.
plasma with a barometric formula.
Okay, so I think that the basic idea is somehow the plasma density is related to the number density of particles in the air. Okay, and at the same time, the pressure, the barometric pressure, is related to the particle number density in the air. So because that somehow as approximation, and people often use the barometric model to describe the number density of the plasma in our atmosphere. Okay, so this is a rough idea. Okay, yes.
I have also a question about the refractional index. So I mean, the air is not vacuum. So only maybe at the top it can be a plasma, but I didn't see. So there must be some dependence on the pressure, so to say, but maybe at these very high frequencies it doesn't matter. So what is your take on that?
Well, as I said, this is just a first order approximation. And actually, in terms of the modeling of the plasma density in the planet magnetosphere, actually, from the literatures, there are different methods. Okay, and here, actually, what we are doing is just take some relatively conservative method, because here the point is when we in this model, when the number density of a charged particle is calculated, and then no matter these particles are free particles or bonded particles, they are all counted in. Okay, but in some literatures, actually, they only consider the number density of charged particles which are free. But here somehow just try to be conservative, so we take this.
No, it's just, so for example, we at DESI, so we have to take into account when we want to calculate the probability of conversion with ALPS. We have to take into account the pressure in the gas, because we have no plasma, we have a vacuum, but the vacuum is not perfect, and therefore there is and this determines essentially the oscillation length. So to say that the oscillation length, in our case, we cannot neglect the QED effect, we can neglect the plasma effect, but we cannot neglect the effect from the gas, so to say. It's an ideal gas. There's the ideal gas formula. Then you can calculate the refractive index. So the plasma mass is the imaginary part of the refractive index, and but the refractive index is the.
Okay, very good. So here, effectively, somehow this effect has been counted in this model. Okay.
Okay.
Yeah. So.
Okay.
Valerie?
Okay.
So you mentioned it at the beginning, right? That this original formula by Raffelt and Sadolsky is derived assuming homogeneous magnetic field, and I mean just there's no spatial dependence or time dependence in any of the quantities. But then you had to do this computation, right, you need the P of omega, right? So the directional dependent conversion probability. So how do you get that? Are you taking the Raffel-Sadolsky formula and just making the B field and the plasma mass and everything position dependent, or what is that?
Okay, we are using this formula, okay, in the sensitivity analysis. Okay. And here I introduce this formula because somehow this formula can help us to establish this physical picture. So.
Right, but so did you use or you do not use this formula?
We use. Okay.
Okay. Okay.
Yeah, there in the back.
About the barometric formula, in my understanding, it is only true within the altitude on the 50 kilometer. So, did you only consider within the altitude, or?
Okay, so here we didn't go to this next order effect. So here we only can consider the leading order contributions. Actually, I would like to bring to your attention, at this moment, we are preparing a follow-up paper. And in this paper, we try to perform a more comprehensive analysis, a more comprehensive study with refined analysis. Okay.
Okay, so.
And so essentially, this is, the first paper is proof of the concept.
Okay, so you made some approximation. You made some approximation.
Yes,
And
just you.
You will update more.
Yeah.
Okay.
With the refined model for the plasma density and also the magnetic field and yeah.
Okay, thank you.
Okay. I think Valerie had another question.
I was just wondering if you would, because here you are looking at sensitivity to stochastic background, right? And then, as you said, right, the ineffective bound is far away. Have you considered sensitivity to transient signals? So something like PPH mergers?
You mean for the... sorry, I didn't get the question. You are talking about the physical...
Right, like here looking at the sensitivity to stochastic gravitational wave background,
true,
right?
Yeah,
and instead, if you've considered looking at the sensitivity to PPH mergers or astrophysical sources.
Yeah, this is true. Okay, we haven't looked into that yet. Okay, thank you. Okay, certainly that is an interesting possibility. Okay.
Camilo?
Yeah, so I just wanted to comment a bit more on all these approximations. So would you say that you are in the most optimistic case when you use these formulas and that all these effects, like modeling properly the plasma, the angular dependencies and all this, will suppress the signal?
You mean?
So because my impression of this is that, so okay, you made some approximations, which I guess is fair, but isn't... this pointing towards like the most optimistic case, and once you include all these, the pressure effects, the angular effects, would this give you less conversion probability?
Okay. Okay. So about your question, the answer is yes. Okay. Just in terms of plasma density. Okay. So. In our paper, okay, in our first paper, actually we performed two analyses, okay, for two different scenarios. In the first case, actually I have a backup slide. Okay, we performed two analyses. For the first one, we consider the conversion probability in the radial direction, over the equator. Okay, and then in this analysis, when we calculate the conversion probability, actually we include both effects. We include effect from plasma and vacuum effect, and then we performed an analytical discussion, and we found out actually the features of these curves can be well explained just using the formulae obtained in the limit of the small plasma effect. Okay, so this means our discussions and our conclusions about the smallness of the plasma effect for the frequency range of interest is valid. Okay, and then in the sensitivity analysis, to simplify the calculations, actually we turn off the plasma effect. Okay, we turn off. This is a test. Okay, and then we turn off the plasma effect, and then we got the sensitivity curves, and then based on our check. Okay, based on our check after the sensitivity analysis, somehow the difference is just of order 1 about the conversion probability. Okay, and then if we go to the and this is order 1 is just for the low frequency gravitational waves because only for that case somehow the plasma effect could be relatively large. Okay, and then for the sensitivity analysis, just recall the limit for the characteristic string is inversely proportional to the square root of the conversion probability. Okay, and then take into that effect into account. Actually, somehow this effect actually is very small. Okay, I think that this is directly related to the nature of the barometric model.
There was another question there.
Yeah, I have a question on the outlook, and if you can go, either page 22 or 21.
Yes.
So when you say Earth here, you are using the magnetic field of the Earth. Is that right, or?
Sorry?
The Earth means that you were using the magnetic field of the Earth, or?
Oh, yeah, we are using the magnetic field of the Earth. Okay.
Yeah, so in this case, since the Earth has an atmosphere, so I'm going back to what Andreas pointed out, you will have an atmosphere, and an atmosphere will have an index of refraction that is different from 1. And your probability is considered in perfect vacuum, where the speed of light is equal to the speed of the gravitational wave. So you're going to have this coherent oscillation of graviton into photon. Did you take into account the atmosphere index of refraction in all cases, Jupiter, Earth, and so on?
Yeah, okay. And this effect, as said, is largely taken into account in the barometric model because somehow for the barometric model, somehow that is based on the total number density of charged particles which are either free or bounded. Okay.
Yeah, I think it's taken into account for the plasma effect, but not for the fact that you are not in vacuum. So we don't have any plasma in our atmosphere or Jupiter atmosphere as well. We have only gas, and presence of gas destroyed the coherent oscillation of graviton to photon.
Sorry, here I didn't quite get you. Okay.
No, just imagine. I imagine the gravitational wave is coming towards my satellite and will convert into photon, but the photon will have a speed that is different from c, and gravitational wave will have a speed that is c, and this coherent conversion of the next, you consider a length, and that coherent conversion can be destroyed because of the fact that the speed of the light has a different speed from c, because it's propagating through the atmosphere.
Actually, from the analysis of the first case, actually we found that the main contribution actually is not from the layer which is extremely close to the Earth. Okay, and for the benchmark scenarios, the altitude for the detector is hundreds of kilometers high. So for that case, I think that somehow this effect is tend to be suppressed because the main contribution actually is not from the dense layer of the air. Okay, and then here actually you can see this effect from this curve. This here, the black curve and the red curve represents the probability represent the distribution or probability density. So here you can see actually as attitude go to the surface of the Earth, somehow they are suppressed. Okay. The main contribution actually are from the region where the altitude is relatively high.
So you are saying just the outer layer where it is in vacuum is contributing?
Have more contribution.
Has more contribution?
Yeah.
Okay.
Okay, I'm happy to see that we have such lively discussions after every single talk in this workshop. This is really great. And I think this is a good moment to thank Tao Liu again